Today we're going to talk about boundary conditions for static magnetic fields. Whenever we talk about boundary conditions, we are dealing with the normal boundary condition as well as the tangential boundary conditions, right? In essence, if we have two different materials, then we form an interface. And on the interface, we therefore have boundary conditions, right? Before I go into the details, let us review the boundary conditions for electric fields. Boundary conditions are really derived from the four fundamental postulates. For electric fields, the first one is divergence of D is equal to the free charge density. Whenever we have divergence, then we know divergence, we have a value, and over the surfaces, we're trying to evaluate the net outward flux, right? So outward flux means we are dealing with the normal components. Therefore, whenever we see this divergence equation, we know that along the boundary, along the interface, we are relating the normal components of that vector field. Curl equation, in contrast, is relating the tangential components, right? Because whenever we have a curl, we need to form a closed loop. So for electric field, curl of E is equal to 0, meaning E fields are conserved fields, and therefore the tangential part of the E field in medium 1 would always be equal to the tangential field in the second medium, right? Now let's take a look at the magnetic field. The first one is we don't have an isolated magnetic basic element, so therefore divergence of B is equal to 0. Now just use your imagination. Just try to view B as D, and now rho is 0. What type of boundary condition can you write down? I mean, we don't really need to go into the details. All you need is a clear understanding to E fields, okay? If B is now replacing D and 0 is replacing rho free, we can directly write down B1n is equal to B2n, right? B is now replacing D, but rho s is now 0. So this is a simple equation you can just write down immediately, okay? Of course, we might not be satisfied with this expression, but we know B is equal to mu h, because now we're dealing with materials. So mu 1 h1n will be equal to mu 2 h2n. Okay? So now you have two different magnetic materials. If you know the field, the B field or H field, it really doesn't matter. If you know the field quantity in one of the material, you immediately know, at the moment, you know the normal component of the second material. Okay? This is coming directly from Gauss's law for magnetism. Divergence of B is equal to 0. Again, whenever we have divergence relation, that tells us how the normal components are interrelated. Okay? All right, so now in materials, this is our new Ampere's circuital law. Curl of H is equal to the free current density. Well, this is really not that much different from this one. All you have to do is replace E by H and 0 by J free. Okay? But the one thing, the knowledge you have is whenever you have curl relationship, you're dealing with the tangential component of that vectorial field. So you can directly write down H1T. Well, you just copy this, right? You move this one to the left-hand side and minus H2T, and that should be equal to your free current density. JS free. One thing you have to pay attention to is here in the subscript, I'm adding this S. I'm adding this S, which is not reflected in the fundamental postulates. Why? Again, boundary conditions comes into play whenever you have two different materials, right? Whenever you have two different three-dimensional materials, then you form a two-dimensional interface. What is a two-dimensional interface? Well, it's a surface, right? Therefore, even though in this three-dimensional divergence postulate, you have the free charge density, so this is still three-dimensional. But whenever we talk about boundary conditions, two materials form a two-dimensional surface, then we need to specify this free charge density is the surface free charge density. Okay? And the current here, let me just jump over. Okay? So two different materials form an interface, and this interface is certainly two-dimensional. It's a surface, right, extending out into your eyes. So the current density that we're dealing with now is the current density flowing exactly on this surface, right, flowing into your eyes or into the paper. Therefore, I have to specify this. The free current density is the surface free current density. Okay? Meaning, if I have a free current flowing here inside medium number 1, but not exactly on the interface, that current density here is not going to contribute into the boundary conditions. You only care about the free surface current density flowing across exactly on this interface. Okay? Now, one thing more, the divergence relation is easy, okay? Straightforward. But the curl relation takes more care. Why? This is your Ampere's circuital law in magnetic materials. And using Stokes' theorem, we can have a closed loop integration, right? And that is trying to evaluate how much of the free surface current you have. So we form this closed rectangle. And we have to make the height extremely small so that we don't really sample these two segments. So we only sample the tangential components along segments C to D and A to B. Okay? So now you take a look. The current that you really encompass, because of this curl relationship, now H is on the paper, right? On this cross-section. So curl, right? Curl of H is equal to J. This means J needs to be perpendicular to this cross-section. Okay? Therefore, it is actually easier for you to note this one as N S. You're dealing with a surface free current density, but you only care about its magnitude, which is perpendicular to the surface, to the cross-section. Okay? Meaning, you might have a surface current flowing in this direction, right? For example, 45 degrees from this screen. But you don't care all of it, you only care about this subcomponent, right? So think about it. This is the reason why, Sn, what did I write? An S? Okay, fine. Sn free. Okay? You're dealing with a surface free current density, and you only care about its normal component. Normal means perpendicular to this screen, into your eyes, right? All right, H1t minus H2t is equal to the surface free current density, but only you're sampling the normal component for apparent reason, okay? Of course, you can write it in vectorial form. Therefore, you have the surface normal making a cross product, and then you have this entire surface free current density, okay? But I personally like this expression better because this is telling you you're only dealing with the current density that is normal, right, perpendicular to the surface. Okay? Any question up to now? These are straightforward, coming from the basic postulates. Okay? But I'm going to leave this on the blackboard because we're going to use it extensively. So now let's take a look at an example. Now we have two magnetic materials, but luckily here we don't have the surface current density. So Js is equal to 0. So immediately, if you don't have the free current density, this is reduced to H1t is equal to H2t. Right? So the two tangential components of the H field in two materials must be the same. Okay? So under this assumption, H1t, H1 field is treated as the known field. You know its magnitude and you know its direction. So alpha 1 and H1 magnitude are both known. So the benefit of boundary conditions is once you know the field in one of the media, you know its amplitude, you know its angle, you immediately know the field in the other material. And if you have a third material, fourth material, you can solve them one by one by invoking boundary conditions. Okay? But now, take a look. Can you immediately tell me, is this figure plotted in the right way? Something wrong here. Something wrong here, right? Basically, in this figure, there is no surface current density. Therefore, we know that since this is 0, H1t has to be equal to H2t. But in this plot, H2t is obviously longer than H1t. So that is an evident mistake, right? So you have to have this ability to tell whether this figure is right or wrong, right? Now that we don't have the surface current density, so H1T is equal to H2T, and the normal condition tells us, well, mu1 H1n is equal to mu2 H2n. So that's the normal condition, right? Exactly the same as we did for electric materials. And then we divide the two equations, then we immediately find alpha 2. Because alpha 1 is known, material parameters are known. So you have alpha 2. You know the angle for the H field in the second material. Once you know the angle, and you know how to relate H2 sine, right? H2 cosine, you can construct H2. So H2, in terms of its amplitude, is also known. So this is a very powerful tool, right? In the future, you might encounter lots and lots of magnetic materials forming lots and lots of interfaces. All you have to do is you know the field quantity and direction in one of the material, and you know all the rest. Okay? This is just a recap of what I wrote on the blackboard. Okay? But the main point is the last slide, as I mentioned on Monday. Okay? Today we're going to use this single slide, and we're going to have discussions in depth. So let us assume we have a magnetic material which is positioned in free space. So this magnetic material is described by this absolute permeability mu. Vacuum is having mu 0. Okay? Let us assume this magnetic material is forced, right, injected with some kind of external magnetic field. Okay? Well, this externally injected magnetic field can have field lines, right, in all directions. So let us use boundary conditions and investigate how the field lines would exit this material, right? So first case, we don't have free surface current density, and this mu, this is not a ferromagnetic. This is more like a paramagnetic, okay? So mu is small. So case number 1. Mu and mu 0. Let me assume this is my H1, okay? H1 vector. So inside this magnetic material, I have externally applied field line, right? Trying to penetrate this material vacuum interface. So this is my surface normal. So this is my angle, theta 1. Boundary conditions are only trying to help you to know what is the exiting angle and the exiting field magnitude. Nothing more than that, right? So now mu is probably close to mu 0, right? Mu is very small, means you don't really see a lot of difference between this interface, right? So now I can decompose. This is my H1T. And because I have no surface current density, H1T must be equal to H2T. So I can just move this one Okay, yeah. So this is also H2T. Right? In the second material, the tangential component of the H field must be equal to the length of H1T. Okay? So at this moment, I already have 50% of the information. All I need is the normal length of H2. Then I know its tangential and normal. I know its magnitude and angle. Right? Okay, this is my H1n. Okay, the normal component of my H1 field. But for boundary condition, what I really care about is H1 normal component multiplied by mu1. And that would be equal to mu0, right? Our second material is now vacuum, mu0 and multiplied by H2n. So let me just multiply it. Okay, let me use a different color. I'll be using red. Okay. This is my mu times H1n. Okay. So as you can see, the length of this red arrow is really not that much longer than the yellow one. To reflect, mu is quite small, right? Okay. And that length divided by mu0 would be the length in the second medium. Okay. Okay. And that I call H2n. Right. I'm trying to make this length almost equal. Yep. So now you know H2T and you know H2n. Then you can draw out, this is my H2 field, and this is my theta 2. Up to now, what can you summarize for yourself? We're not doing anything new. We're only trying to repeat what we just analyzed, but using drawings. Okay? We don't have surface current density, and therefore H1T is equal to H2T. But as I progress, you should be thinking, how can this angle, theta 2, be related? Or the magnitude of theta 2 as compared to theta 1, can theta 2 be larger than theta 1? Think about it. The question is, theta 2, theta 1, you have three choices, right? To my best knowledge, you have greater, equal, smaller. Right? The entire purpose here is to give you a very strong impression. When you have fields coming out of a material with larger permeability as compared to the second one, the exiting angle as compared to your incident angle would have one decisive relationship. Okay? So in this case, here, because due to the fact mu times H1n is equal to mu 0 H2n, this mu is slightly larger than this one, so H2n, let me use the right color. H2n is mu 0, mu 0, mu r times H1n, right? The absolute permeability for my magnetic material is mu 0, mu r. So basically, these two cancels. Now, as you can see, whenever you have fields coming out of a material with larger permeability, it's always making the normal component of the H field in the second medium to having a larger amplitude, right? So now can you tell me, can you come up with a decisive conclusion? How are theta 2 and theta 1 related? H1t is equal, right? H1t is equal. What's determining the angle is the normal component. If this guy is larger, it's making this angle, answer me, smaller, right? So this is what I call self-learning, right? As I am introducing these concepts, you should be asking, well, in the end, all we care about is the magnitude and the angle. Just by one simple analysis, you can know that, well, this mu is bigger than this one, then theta 2 needs to be smaller than the incidence angle.